Okay, so we'll start with module 3, and I know module 2 has been very large. Module 3, 4 and 5, all three of them are not so big, and also module 3 is not so mathematical and technical. So there might be a little bit of math involved, but it's not going to get into the complexities of computer science and other things. Okay, so you will find it way easier. So module 3 is risk and risk factors. So slowly from the toolkit we are getting into what kind of risks are going to be part and parcel of AI related use cases and implementations, etc. So the first thing which we are going to discuss today is going to be about fairness and the bias. Okay. Now fairness and bias are directly proportional to each other, or you can also say indirectly proportional, because if a system is more fair, it is going to be less biased. Okay, but the incorporation of bias and fairness will go hand in hand. So you create a system which is less biased, it is going to be more fair. So we are going to dig these terms a little into more depth and trying to understand what fairness and bias is, and there are some definitions that Garp will illustrate. I am not going to go into the illustrations that it will say that bias is some kind of a systemic error in the system. Okay, so if there is a systemic error in your model, that is how most of your people are going to define the bias. But the intent, my intent at least, is not to just read the definitions and put it here, but to make you understand what these terms actually mean. So, and we are not going to talk about bias and fairness side by side. We'll talk about both of them together, because as I said, that if you try to bring a system which is fair, so when I say fair, it means that it does not prefer an individual based on one or many criteria. So the criteria can be gender, it can be your race, or it can be your religious affinity, or even your nationality, which is kind of a question mark, but at least some of these demographics like your gender and race and religion should not impact the decision of your model to be a fair system. Okay, and if there is a system which is fair, it does not create a bias in terms of gender, race, etc., etc. So that's how it is. And so let's start with a very, very important principle. It's I think it was given by Aristotle, which says that to make a system fair, there is a principle which says treat like cases alike. Okay. So if you look at it, this is a very, very simple kind of hypothesis, and this becomes your kind of a Bible for all the postulates or all the theories that we can talk about fairness and bias. So if there are like cases, you should treat them alike. Okay, so that's the entire theory, and that's something that we need to bring together. So now there can be two things. One is individual fairness, and the other one is group fairness. Or okay, so what happens that when we start talking, when we start speaking, we will start saying that systems should be made that it treats individuals alike. So if tomorrow you write a GARP exam and there is somebody else who is writing the GARP exam in US, okay, and you are writing this in, say, let's suppose in India, and there is a third individual who is writing the GARP exam in, say, Gaza, okay, I assume there is a center there. So your probability of passing or failure, it all depends upon the your knowledge, and your knowledge is a factor of how much of hard work or how much of intelligence and other things you have. And it will treat like cases alike. If somebody is scoring, say, X marks out of the total, or X percentage, so X out of 100, whether it is here in India or in the US or in Gaza, the decision of passing or failing of that individual depends upon the merit of that individual. So that's the individual fairness we start talking. But then if you see, and in this example, and we'll talk about more examples, let's suppose we talk about an admission to a university. Okay, so when we talk about admission to an university, and it gets there are applications from various people, and then if we do a setup like GARP, some people, of course, some people will get through, but then there is the nature has created a bias in this societal ecosystem, that not everyone starts at the same start line. Okay, so not everyone starts same. So there are people who are rich kids or rich people who have abundance of resources, and let's suppose we are talking about admission to a university which is like an MIT, or probably which is like an IIT in India or MIT in the US. Okay, so now what happens that there are socially weaker sections in the society, so people who have some kind of who have been through some kind of social injustice, and then there are because of the way the society has come up and the way we have evolved, there are some biases on the basis of gender also. So women are not given so much of opportunities, at least in developing countries. And then if we talk about transgenders, etc., they are also they don't start equal. And then there can be very, very economically poor people who are below poverty line. Okay, and then there are general people, general people who have good resources, good, no societal issues or no societal atrocities, or nobody treats them unequal in the society, and they also have enough money and other resources. Okay, so now if we treat them equally, then it is not fair to some of these individuals, because they need to put in more effort to reach to a stage where somebody who is not going through all of those extra problems will have to go through. So this creates a kind of a debate that what do we do, how do we fix this problem? Okay, so we're still trying to understand the fairness and the bias principles, and we'll start with, so if you remember, we spoke about when we went into module 2, we were talking about this kind of a confusion matrix, where they said this is true false and this is also true false, this is your, let's suppose, predicted, and this is your actual, and then based on the numbers that you get here, this is your true positive, this is your false positive, this is your false negative, and this is your true negative. Okay, we created terms like accuracy, precision, recall, etc., etc. So we'll use these terms again. So we start with something which is called as demographic parity. Okay, so what demographic parity means is that that if there is a particular group, the probability of getting selected, let's suppose we are again talking about that university admission, where people from various countries, people from various genders, people from various other factors are giving applying for admission. So it says that the probability that your prediction is 1, probability that you predict somebody, and let's suppose the category or the parameter is A. So let me say A equals to 0 is same as, I'll try to explain this a little more, but I'm just trying to go step by step. Okay, that this is 1, A equal to 1. So this is this. So y hat is your probability of getting through in admission in that college. Probability of admission. Okay, and A is your, A being 0 and 1 is probably your societal injustice. It can be your gender, whether it is a male or a female. So your model's predictability to say yes, get him through, get her through, should not be dependent upon the factor that is taken into consideration, whether it is societal or whether it is anything else. So if your admission rate is say so and so percentage for male, it has to be so and so for female. So now there are issues with respect to implementation of this demographic parity, because what it means is that if your let's suppose if it's very hard to give examples also, because people can take it otherwise, but if there is one group of individuals and the average education or the average income of those people is, let's suppose, very less, and then there is another group of individual whose income is on the higher side, then if I try to make a lending system or a credit accessibility system, credit assessing system for this group A1 and A2, it is difficult to say that we will only give 30% of these individuals, and 30% of these individuals will also get through. It's very difficult to implement this without compromising on the merit, or when we said treat alike places alike, or let the merit be the only standard. So that's the demographic parity. Let's go one step ahead and let's talk about one more thing, which is called as predictive rate parity. Predictive rate parity. Okay, so just to re-emphasize, demographic parity means that the probability of the model to say yes or no, let's suppose the model is only talking about yes and no's, and then the probability of the model to say yes is same whether we are talking about one group or the other group. Okay, so that's the demographic parity. What happens in predictive rate parity, we'll just extend this, we'll talk about the formula first, and then we'll so it is more about your precision. So if you remember precision says that it is your true positive, it's a ratio of true positive to the ratio of true positive and false positive. Okay, so it says that if you say that if I'm making a statement that out of there are 100 applications which I'm saying loan should be granted, and after a point of time, let's suppose after the tenure of the loan, we find out that only 70% of them were worthy of loan, or 70 cases were worthy of loan. The rest of the 30 could not pay back or do whatever it is. So that means that 30% were false positive. Most of the time we'll only come to know about this once the event has happened or once the default has happened, etc., etc. But this is what the precision on a higher level means. So the PPV, or the predictive rate parity, is your probability that your output should be when, this is about this 70%, which happens only after the event has passed, provided that your y hat is also 1, and let's suppose your this is a kind of a group, so I'm just using the letter A here. So if you predicted this as yes, and it is yes, should be same as your y equal to 1, y hat equal to 1 for a equal to 1. Okay, so this means that which is a little easier than your demographic parity, because now what you are saying is that the accuracy of your system in terms of precision needs to be same across various demographic or various other features. This a equal to 0 and a equal to 1 means that. So let's suppose this a is gender. Then now we are not talking just about your prediction, we are talking about y, which is your actual value. So it is more on the ratio. So if it is 70%, if your model is 70% precision overall, it needs to be 70% for women and it needs to be 70% for men. So it needs to be it should not it should not say that while this is the precision is overall precision is 70% or whatever is the overall precision, but the distribution of that precision across various factors is not the same. So that's your predictive rate parity, which is which is slightly different from demographic parity, because in the demographic parity we never spoke about this value. One more, and probably then we can do some regular discussions, or I can just close this discussion here. I will probably create smaller videos for module 3 because the topics are more distributed rather than math intense and things like in module 2. Okay, so the third thing that you should know is equal opportunity. And GARP will smartly ask you about a scenario, and it will say whether it is a kind of a demographic parity, whether it is an equal opportunity, or whether it is predictive rate parity. Okay, so you need to understand these concepts very thoroughly. You may read more, you may take more examples from the book or from any other place, but this is more on the side of recall. If you remember our earlier videos, probably module 2 chapter 8 or 9, where we were talking about how do we evaluate some of these machine learning models, at that point of time we were talking about recall. Okay, so recall is nothing but the ratio of true positive upon true positive and false negative. Okay, so what we are trying to say is that if there were 100 cases where the patients came and they had they actually had cancer, so there were a lot of people that went to the hospital, maybe hundreds or thousands or tens of thousands, and out of that 100 cases, which is like your true positive or your actual value of the positive class, and my model was only able to get the 95 cases out of these 100. So 5 were, that 5 is false negative. Okay, so so I'm more interested in recall here rather than precision, and in certain circumstances recall is, as we said, that in cases like cancer detection, recall is more important. So even if I get a false positive, I'm okay, but I should not get a false negative. So mathematically I can put this is as probability that your y hat is 1, knowing that your y is 1. So it says that your there is some demographic which is equals to 0, and then I'll say y equals to 1 needs to be same as the probability that y hat equals to 1 and your a equals to 1 and y equals to 1. Okay, so this is what we are saying, that the probability of the model to predict yes or no, knowing that it is from a particular demography and knowing that it is a positive case, should be same across various groups, whether it is group 0 or whether it is group 1. So if you look at equal opportunity and your predictive rate parity, there is just a shuffle of parameter. This comes here, this goes here, and this comes here. Okay, so that's how there a little bit of shuffling has happened, and that is the key difference between precision and recall. So in this particular case, exactly what we are saying is that the cancer detection for, say, a group of, say, Africans and the group of, say, Europeans should be same. So if your cancer, if there is an device or an algorithm or a clinical test that gives me 95% of recall in case of European people, it should also give me 90% of recall in your African people. Okay, it should not be that because you were doing more testing on Europeans, or there can be multiple reasons of how a bias or a an algorithm not being fair actually percolates into a system, which is going to be our next reading. But let's forget about the how part of it. But we talk about equal opportunity, talks about the effectiveness of an algorithm to get the same recall indifferent of what group of individuals, of what group it it belongs to. Okay, so those are the things that should end our bias and fairness reading. There is a small discussion that happens in the end, which Garb doesn't get into the too much of details, but it says that there is a trade-off. There is a trade-off between individual fairness and group fairness. Mathematically, it is impossible for you or for anybody to become individually fair and to become group fair as well. So the minute you start to become individually fair, if we make merit as the only system and say that let's suppose we all submit research papers in some of these top conferences, A and A star conferences like EACL, or I mean in the NLP world it is ACL and the conferences like that, and it is blind review, so you don't come to know whether it is coming from India, whether it is coming from a rich person or a poor person. So the selection of those papers is individually fair, because there is no inclusion of demographics into the paper that is being sent for publications. But in this particular scenario it is good, because most of these publishing houses, they want only the most innovative, most groundbreaking researches to be published. Okay, so it doesn't matter to them that somebody is doing more effort if say the compute resources are not so much of available in say Asian or African countries, and it is difficult for them to build a system like ChatGPT or something like that. So while it is individually fair, it may not have the fairness from the group perspective. Okay, and most of your government backed schemes, or anything that has an element of socialism, will always have some kind of advantage or given to weaker sections, or it will always have uh, the group fairness, that if there is a particular government school or a government policy that needs to be used by a group of individuals, it needs to be independent of the financial profile, the social profile of an individual. Okay, so I'll just take a pause here, and in the next reading we'll start talking about how does the bias get into your ecosystem. How there can be bias in the data itself, there can be bias in the algorithm itself, there can be bias in the way somebody is writing the requirements itself. Okay, somebody can write an requirement which itself is the start of the bias. Okay, there can be intrinsic bias and there can be intrinsic bias. Intrinsic means that the person who is writing the model or writing the code, intentionally or unintentionally, he has created the bias. And extrinsic bias is that if your data itself, which is used to train a model, has a bias, because if you look at the data, if you look at, let's suppose, your face detection kind of data, if it has 70%, 80% of people as whites and only 20% as blacks, it is definitely going to be more effective for whites. So it's a kind of a data bias. If your LLMs have 70% or 80% or even more of their data in English, okay, and if there is only, let's suppose, 1% or less than 1% of data for some very very remote language, let's suppose Tibetan, okay, so it will be definitely be biased towards more resource rich languages. So we'll talk about those things in the next reading.